Good afternoon, everybody. Thank you for coming along. So, I'm Christopher Biggs, and I've been involved with embedded systems since my first professional job about 20 years ago. And nowadays, I'm a consultant specialising in the Internet of Things, which is the new name for embedded systems that don't work properly. So I work with companies that develop IoT devices to help them choose the right technologies and practices to build and deploy their products. Now, I've spoken in the past about the state of security in IoT, and while I agree it's pretty awful, I'm not pessimistic. I made some predictions about how bad things could get and what type of action that I wanted to see, and the bad and good news is that these are coming true. So I'm seeing the space rapidly mature and the right things are being done to address the challenges. I've spoken many times about what I call the Internet of Scary Things. Most recently last month at IoT Sydney. And that presentation is about how it's like the Wild West right now and why DevOps is really a must-do for IoT. Traditionally, hardware has been developed carefully and conservatively and had long life cycles. Now, IoT brings the contradictory requirement of products that are set in stone, sometimes quite literally, but which connect to the wild internet where sometimes a day can be an age. So this talk is going to be about the how you can apply best practices from grown-up computers to the challenges of building and managing internet-connected autonomous devices. So I've called this talk DevOps for Dishwashers because recently the tale of an internet-connected dishwasher made the news. A lot of people laughed because why would a dishwasher need to be on the internet? Well, it took us about 10 years to go from personal computers being networked only at need to us considering any computer that isn't networked to be broken. So I expect the same for every other electric appliance. In the long term, I think the very word computer is going to disappear because everything will be a computer. Software, as Mark Anderson said, will truly have eaten the world. And this will have a lot of effects, but the one I want to focus on today is that we must really rethink our concept of quality in the embedded space. The price of an amazing future where everything can interact with everything else is that everything might interact with everything else. So before I go too far, I want to define what I mean by DevOps. This is one of those technical terms that has been misused so much that it's dangerous to use it without confirming that the listener hears what you mean. So for me, DevOps is not a thing you do, it's a way you do things. DevOps engineer is not a job title. There's no such thing as a DevOps team. It's an easy mistake to make. I, in fact, once held the job title of head of DevOps. But what DevOps is accepting that development and operations are part of a spectrum and that distinguishing between them is counterproductive. So my full definition of DevOps is evolving a culture and a tool set that empowers everyone to effectively maximize value through radical transparency and extreme agility. So today I'm going to look at how we pay the price of this connected future. The body of the presentation is about the practical things that you can do to build quality products for the Internet of Things. I'll look at the life cycle of an IoT product from inception to retirement and what you can be doing to get the best outcomes at every stage. The areas I'm going to look at are, firstly, choosing platforms that support rather than hinder quality outcomes. Secondly, shaping your development and quality practices to foster agility while preserving reliability. And third, working with your data in ways that promote interoperability and reusability. So just before we dive into that, I want to look at the universe of discourse. In just 70 years and 10, the span of a single human lifetime, we saw the ratio of computers to people increase by around 1 order of magnitude per decade. If you were a fresh-faced undergrad when Konrad Zuse was building his Z1 in 1936, then you could still be around next year to celebrate your 100th birthday. Fast forward 30 years, 1960s, around 10,000 devices per person, sort of one mainframe per large company. A decade later, we've seen another 2 orders of magnitude increase. Computers have become indispensable to our civilization but this is not really widely recognised. Another decade, another 2 orders of magnitude. That's like the inflationary era of the early universe. Things are growing faster than we can really comprehend. There's a school of thought that says that the desktop computer created the 1980s investment trading boom because spreadsheets allowed people to do things in business that they'd never done before. Jump to the 1990s, computers are starting to diffuse away from people. They're eating into the fabric of our lives. If you're old enough to remember growing up without a smartphone, then you'd recognise that young people today simply wouldn't understand what life was like before that era. Today, we're starting to lose count of how many computers there are. Very soon I think we won't even bother to ask the question. And that trend is not over. So in the next decade I expect another decoupling. And at some point after that we're going to completely stop counting. Everything will be a computer. Everything. Hence the Internet of Things. A world where humans are a 0.1% impurity in a sea of machine life. If we're wise, we'll make friends with the machines when they're babies, because I don't think we'll beat them in a fair fight. During the early part of the 20th century, one analyst predicted that an oncoming apocalypse where civilization would grind to a halt because every single available unmarried woman would need to be employed as a telephone operator. And no further rollout of the telephone network would be possible. Of course, now we have robots running the switchboards and even making and answering some of the calls. Instead of having a sizable fraction of the workforce operating the communications network, we have millions of people in less developed countries trying to sell those people life insurance over the telephone because the cost of communication is practically zero. So if you wonder how we're going to curate and maintain 1,000 devices per person, you're making a similar kind of category area. Strategy is about adapting your behaviour to circumstances. When a computer cost 3 months' wages, you shepherded it carefully. When computers cost less than a cup of coffee, they become consumables. They're sheep, not sheepdogs. The unit of management becomes the flock. Now, I could go on for quite some time about the security landscape in the Internet of Things, and I have spoken about this in the past. The one slide précis is that bad people want to break your stuff. It doesn't have to be many bad people. Another side effect of that zero cost of communications is that if you're a terrible person, the 21st century is a target-rich environment. Now, I don't really want to go off on a tangent about security, but I find that the underlying causes of security problems in the IoT are an instructive microcosm of the wider challenges. Last October, the Mirai worm spread around the globe because of well-known default passwords that never get changed. This month we learned that the CIA has been able to insert spyware wherever they like because some software developers found it convenient to put backdoors into communications hardware. Choosing expedient but fragile programming tools brings consequences. The pattern here is a lack of professionalism and forethought. Moving on, in April we got the endlessly entertaining story of the compromised internet dishwasher, which demonstrates how many developers aren't trained well enough to avoid common and completely avoidable pitfalls. The downside of ubiquitous communications is that there are no safe spaces. June's WannaCry malware outbreak showed us that when everything is software, everything has to be maintainable. Last month's second coming of a much more damaging successor hammered that point home. If you can't fix it, it's no longer safe to own it. Firewalls and even air gaps are not sufficient. A final anti-pattern I want to touch on is if you sit in the middle of the road, you'll get run over. Quality procedures that worked last year might be a liability this year. It turns out that the government software quality guidelines that have been applied to election security in the United States delivered almost no benefit and some potential detriment because they largely focused on constraints that aren't relevant anymore. These guidelines for safety critical software prohibited things like exceptions and recursion, and that's more about preventing your space probe from overflowing memory and crashing into a planet than it is about software quality on modern processors. So let's summarise what I think a response to these challenges should look like, and then we'll go into some detail on each point. First, choose the right platform and tools. Next, make your identity and security part of your framework so that you only build it once. Automate everything you possibly can. Design for testability. Train your teams, share skills, watch YouTube videos, get consultants, come to conferences. Whatever your budget, there's a way to improve your outcomes. And lastly, maintain awareness and use that awareness to respond rapidly. So let's talk directly about platforms. Jez Humble, who literally wrote the book on continuous delivery, gave a keynote right here in this building at Agile Australia in June, where he told a story about HP's printer teams. Their cost of engineering was spiraling, but their quality was awful. And part of that reason was that they were spending over a quarter of their time just rewriting existing software because pretty much every printer model used a different processor. So they made the choice to move to a common architecture and reduce their re-engineering cost. And that meant that some printers had a more expensive processor than they needed, but the savings far outweighed that. My point here is that every hardware business has a person whose job it is to look at every component and ask, can we delete that and save half a cent per unit? And we need to resist that mindset. This is a person who's empowered to remove customer value. The correct question when designing your hardware is, will this hardware platform add value in terms of resilience, longevity, and supporting software quality? So your platform is part of your DevOps team. Your goal should be to select a platform that supports your DevOps way of doing things. So while selecting and building the hardware is by far the easiest part of the IoT lifecycle, it's the foundation that facilitates the rest. That means that openness and friendliness are the first things you should look for. Select a processor and platform that's got good development tools and will be around for a long time. Now, thanks to the drivers of Android phones and TV media boxes, there's a huge variety of ARM systems out there which are similar enough that hardware differences aren't really important. So you can develop to the one architecture and then select an appropriate board from $5 up. In my projects, we work a lot with the Raspberry Pi as the development platform. This is a $35 computer which brings the convenience of a huge selection of platform tools and a great developer community. And we can use those in the lab, we can use them in our continuous integration systems, and even for the first 100 or so production units. There's a wide selection of compatible lower cost designs to buy or build for mass market production. Here's one that starts at about $7. So the same goes in software. Think about what happens if news of a nasty bug breaks out on the internet. The top tier vendors are probably going to have a patch out in a couple of days. If you pick some hipster Linux distribution that has 50 users and 1 maintainer, you may never see a patch. You want your tools and your systems to be a convenience, not a source of pain. If you're using a mainstream OS variant, and for IoT that pretty much means Red Hat or Debian, then there's a critical mass of users that acts as a quality filter. There's not likely to be some hidden problem that you can't solve. If you're the only company in the world using some niche distribution, when you run into trouble, you're on your own. I also think it's important for devices to be online as much as possible. Now, power and network constraints may mean that these devices can't afford to be online all the time, and that's tolerable, but you do need to think about how to support DevOps processes within these constraints, and I'll come back to that later. I think you should plan to have two-way communications with your devices. Forget about the low-cost one-way communications channels. They might be cheaper, but in my experience, you're going to regret it. Make sure that you have a way to locate and identify every device, even if you don't think you're going to need that. I'm talking about putting some kind of display on a device, even if it's only a single light-emitting diode, so that, and letting devices determine their own location, either by GPS or more coarsely via cellular or Wi-Fi estimation. I've heard more than one story from the world of oceanography where probes go missing because people rescued them and they get found out the back of a dive shop or in a junkyard. And use a remote management platform. At the very least, you need a secure way to upgrade and shut down your devices. I'm recommending using an agent-oriented data center automation tool like SaltStack. I'll give some examples of what I've done with this tool later on. The right tool is going to kill two birds with one stone. You can use it to construct your master configurations in the lab, and then you can use it to manage the devices in the field. So we chose some hardware and an operating system, and we've installed at least one blinky light. Now we have to make it blink. If I could give you one piece of information today, it would be use a serverless architecture in your cloud services. serverless doesn't mean there aren't servers. It means you don't have to worry about them. I'm putting together a global building management system that so far doesn't rely on a single fixed server, and that's including the whole CI pipeline. I want you to take a good, hard look at what programming platforms you use. Don't use something just because everybody else uses it. Programming has entered an era where the ability to be rapidly up and running thanks to an ecosystem of open source parts is really revolutionizing the craft. One of the most important things to look for is a healthy ecosystem of actively maintained components. JavaScript, Go are two languages that I find particularly notable for this in that they've got component search engines that help you understand who else is using a component. Are you the only person left using this, or is it being used by somebody with a lot of resources to keep it running? Looking deeper at JavaScript, it could be said that JavaScript rules the world. It's arguably not the language that anyone would have chosen to be number one, but it's there and it's getting better every year. You can now literally run JavaScript from chips to cloud on a $2 microcontroller all the way through to your cloud services. It's the only language, as far as I can tell, that has got common support against Azure, AWS, and Google Cloud. JavaScript is also a good way to write user interfaces. At the moment, I'm working in Elm, which is a strongly typed meta language that produces highly reliable and quite pretty management interfaces. Don't write your own user interface components. There are so many good options out there. Every network router ever looks terrible, and I wish they would stop reinventing the wheel. I'm using Go for one of my larger projects. This is a good fit for container environments in particular because it produces executables that are self-contained. You don't have to go and look at a crystal ball and figure out what shared libraries you need to ship. There's built-in cross-compilation support, so you can work on Windows, Mac, or Linux workstations wherever you're most productive. My CI pipeline can run on stock cloud systems and spit out ARM native containers. I find Go is a very pragmatic language. Although it looks a lot like C, you find working in it is more like JavaScript. You don't need to worry about memory or pointers, and the type system actually helps you to write reliable code. Now, I coded in C and such like for a long time, and I really don't think there's a good case for widespread use of these tools anymore. It's simply far too easy to write brittle or insecure software. Modern languages have learned from these drawbacks and provide a really effective safety net. Shell scripts in particular are very tempting, but when you are dealing with malicious users, the attention to detail needed to manage your inputs safely takes all the convenience out of using shell scripts. Now, frameworks are important for IoT because there's a lot of foundation behaviors in common between devices. Given the time and budget pressure on low-cost devices, you don't want to waste resources on addressing the same problems over and over, or worse still, not addressing them well at all. So I'm using Amazon's ecosystem in a number of projects. They've really thought about what IoT means for device management. Major challenges for security, intermittent connections, data collection are pretty much solved for you. When scale becomes an issue, you have a system called Amazon Greengrass, which lets you move from a centralized system where everything talks back to one cloud service to a more decentralized architecture where you might have a building level or a floor level element which is under the control of your AWS. If you look at the awful usability of many home automation products, you'll see that the vendors of these products have implemented basic behaviors badly where they could have just gotten that work done for them if they'd adopted the right framework. These are some frameworks that I like. The good news for us is that there's a lot of vendors going hard at this problem, and most of the big frameworks are very well done. But there is a learning curve. You're initially going to look at these frameworks and tell yourself, I don't need all this complexity. I can just skip to the end. But particularly in the maintenance part of the life cycle, a good framework will pay you back. Now, I've gone on record and saying that you shouldn't just screw a Linux server to the wall, nor ship software that you don't need. So here I am advocating using a common mainstream hardware and software platform, which breaks both of those rules, really. And containment is how I reconcile those constraints. Software containment causes me to limit the interactions between my parts, which helps with security and complexity concerns. And the consequent loose coupling between the parts lets me reuse components more effectively. Now, Docker is the containment engine that everybody knows. There are 3 or 4 others now in the Linux space. But to be honest, I haven't done much more than kick the tires on the others because Docker is the one that has all the major cloud vendors on board. And what I suggest that you do is you set up your continuous integration pipeline to produce Docker images as the output of your software pipeline, so that your code reviewers and your testers can get the exact artifact that's going to be deployed, and so that your orchestration tools can push these artifacts down to your devices across the internet. So testing is probably the single most critical point for DevOps. The goal we're striving for is more frequent releases, and in order to meet that goal, you really have to address the human cost of testing. The most important point here is to actually do the testing, to structure your enterprise in a way that provides fast and easy access to test environments. Ideally, anyone who wants to test can click a button and have a fresh environment in minutes. If it takes days of work to provision an environment, nobody's ever going to do it, which means some testing will never get done, or your test system will be out of date. So you want to have fast spin-up and replacement of services. And worse still, if you're not deploying new environments on a regular basis, you might get to that moment where you need to do it in a hurry and discover that nobody knows how anymore. I've actually seen that happen. So in order to facilitate testing, you need test data. So you need to pay a good deal of attention to ensuring that you develop test data generators alongside your code, because making it painful to test will result in painfully bad testing. Now, actual research data shows that the sooner you find a bug, the less it costs to fix. If a developer never makes a mistake, it doesn't cost anything. So that's the first place that good tools and the right languages pay off. If you find a problem during coding, that's where pair programming and code review pay off. If automated testing tools find a problem, then at least you haven't wasted anyone else's time. Now, you can tell developers, always run the test every time before you commit. But in my experience, pixies will fly out of my ear before that happens. So whatever central CI system you have needs to fail cheap. You do the fast test first and the slow tests later, so that whatever's most likely to fail is up front. Once a change merges into your code repository, the costs of fixing problems start to multiply. You've consumed the time of the person who found it, then the developer who fixed it, and then the person who confirms it's fixed. If you make it to integration or release testing, then maybe you have to go back and redo other work and redo testing and possibly reschedule your release. And if a problem makes it into the hands of your customers, we're talking about literally hundreds of times more to cost to fix than if you'd found that problem on day one. It is true that comprehensive automated testing takes time and money. Studies show it costs around 30% more, but brings a 90% reduction in defects. So if your automated tests catch one bug a week, and that takes the developer an hour to fix, and otherwise it would have reached customers, then those tests paid for themselves twice over. Now, when you're working in IoT, you're probably not running an x86 CPU. So how do you compile and test for various embedded CPUs in your continuous integration pipeline? Well, good language choice and containers come to the rescue here. If you're working in Go or Node.js, you'll find that you can run your code on pretty much any platform and build your distribution artifacts on any cloud server. Emulators have gotten really good too. You can spin up an ARM emulator on a PC and boot it up just like a virtual machine. It is quite remarkably easy compared to how hard it was 10 years or so ago. But you do want some real devices, of course. So where you need to compile or test on your target system, if you choose the ARM architecture and Linux, this means that your systems can pretty much integrate right into whatever CI system you're using. Now, I happen to be using GitLab because it was one of the first systems to build the automated testing tools right into the code repository. But now, over the last few months, GitHub and Bitbucket have all that too. So really, in terms of CI systems, go with whatever you know. And the way I do this is I tag the jobs which must run on an ARM as requiring ARM, and then configure those ARM workers only to run those jobs, so that everything else happens on an x86. So out of this complete pipeline here, only that one test on Pi job runs on an ARM, everything else runs on a Amazon EC2 instance that is just stock Linux. So first stage of my pipeline is a pre-compilation test that runs code quality checks and static analysis. Second step is compilation. Now, I am building for 2 architectures, but that's all happening on the same machine, and that's generating Docker images that contain binaries for ARM and x86. That means that I can do some testing on x86 and not have to use slightly more cantankerous embedded systems. And here's where that ARM CI worker gets used. In the third stage, we run some testing on x86 and we run the testing directly on the ARM system. And so I have a number of Raspberry Pi systems which sit in the office and connect to my CI system. Now, the final stage is deployment. And because I'm using Docker, it's possible to have multiple images in each registry for a particular product. So all the side branches for feature branches and developer test branches get pushed up with a tag of the developer's name. The master branch pushes to my main registry, and that gets tagged as staging or production. And any commit to the master branch will automatically push to the staging repository and require manual approval to push to the master repository. So when you want to do a release, you can test it on your staging systems, go, yes, that's good, hit the button, goes out to production. And you can build all that with as little as 2 machines. But if you need hundreds, then it'll scale perfectly well. And this is pretty much the entirety of all the configuration I needed to set up that pipeline. I use worker tags to force certain jobs to run on ARM. I really don't like to put too much configuration in my CI system because it is important to be able to run the tests manually from your workstation when you want to. So most of the logic is actually in the makefile and the test scripts. And even with the best of intentions, temporary developer backdoors stick around. So the way I deal with that is I generate a developer debug version of every software change and a production version. You can't really out-lazy programmers, and I say that as a 25-year programmer. So set up your system so that every CI build gives you that lockdown version and the developer-friendly version. You don't really ever want to hear a developer say, I'll just hack this into the production build and then take it out later. Edith Harborough this morning told several stories where lab code left in production builds cost hundreds of millions of dollars per incident. One of them was in fact a feature flag named "Do not enable this flag," and guess what happened? The last thing about testing is you may want to set up daily regression tests, performance comparison tests over long time bases, and you can do this by dedicating hardware to those jobs and basically nailing it to the wall. So you made it to a release. Now there's 10,000 instances of your code out there, and they're up a pole or buried under asphalt or fired into space. So don't stop testing. When we run our tests in production, we call them dashboards. Bond villains are big on dashboards. You know, the funny thing is I set out to find a Bond movie image for this slide, and they all looked rubbish compared to reality. It seems that a generation of nerds have created a future straight out of fiction. That image up there is from Hootsuite's operations sensor, and that only shows about a third of the room. A social media company is now more impressive than a global supervillain. But you don't need all that rubbish, because who's looking at those screens? I count 63 screens in the full-size image of that, and 4 people. That's 16 or more for every person in the room. We need machines to watch our machines. So the simplest approach is gauges that have a red line and an alarm that goes off when the needle hits the red line. Next level up is what I call artificial stupidity, which is you ignore everything which is provably safe, and then you refer the things that are maybe not to people. And finally, you can actually apply machine learning. In June, the most recent release of Elasticsearch actually has machine learning anomaly detection for log analysis. So it'll look at your application outputs and tell you whether or not things are off the rails. So you've got some tested code, it's been encapsulated in a container image, and now you need a device on which to run it. Don't turn into the trap of turning yourself into a robot. Some people say that as a programmer, you should automate anything that you ever have to do more than twice. Well, I'm going to save you those 2 times and say, automate it from iteration 0. If you are setting up a system to become the base operating system for an IoT device, you'll find pretty soon that it's quicker to use an orchestration tool than it is to do it by hand even once. And anyway, you were wrong about only needing to do it once. And that's just something that I've seen over and over. A project starts with developers putting together a quick prototype, starting from a blank OS card, installing some tools, editing the configuration, taking some notes on what they did probably. And then it's 6 months later and there's a new version of the OS and nobody really remembers how to get from a clean OS to an app-ready platform. And that is how many embedded devices end up running 8-year-old kernels that are riddled with bugs. So what's a better way? Again, there's a hierarchy of technologies that you can use. You could set up a target machine on your network, SSH into it using an orchestration tool. I happen to use SaltStack over SSH. You could run your target machine in a virtual machine or an emulator, so you could use Vagrant or QEMU. Or you can in fact put your target machine in a container and use Docker files to do the setup. Basically, you pull yourself up by your bootstrap. The system that I've built uses SaltStack serverless mode, which means your installation system will use SSH to connect into a blank target system. It will install some components on it. And then once the management agent is on the system, it talks to the management agent and does the rest of the process. So the first part of my process is converting a vendor image to a product base image. That runs through a bunch of repetitive stuff that nobody wants to do by hand, setting up time zones and locales and all that sort of stuff. And at the end of that process, we join up to the output of the CI pipeline. So CI takes source code and turns it into tested Docker images. The orchestration system takes a tested Docker image and drops them onto the operating system image that this process prepared. So we've closed the circle. We have continuous deployment. And at that point, you might be thinking, this sounds a lot like a platform as a service offering, like OpenShift or Elastic Beanstalk. And you'd be right. Those systems provide a pre-prepared operating system which you don't really have a lot of control over, and you just drop your code onto it. And there are options in the IoT space that do exactly that. So one of those is a project called Resin.io, which provides a base Linux image that connects back to their cloud systems. You push your code up to their Git repo, their system compiles it and pushes it down as a Docker image onto your registered devices. And they support a number of common embedded systems, and they take requests for which ones to add next. So, for example, I'm beta testing a new device for them at the moment. Another system that I quite like the look of is Amazon Greengrass. If you're familiar with Lambda, Greengrass is basically on-premises Lambda. So you use the same mechanisms, but instead of deploying to an anonymous container that you never see, you're deploying to an embedded system that you nominate. In the microcontroller space, I like another project called Mongoose Os. This one offers the same sort of facility, but without the central cloud repository. So you compile your code to a zip file, you upload that zip file to a device, and it verifies and installs the content. Now let's zoom in on that verifies part. How do you permit secure remote access to your devices? Now the obvious way is with X509 certificates as used in the World Wide Web. only the public key infrastructure for the World Wide Web is basically a global protection racket. So the hard part of public key cryptography is authenticating the remote party. That's what the certification authorities are there to do on the web. The alternative is two secret agents exchanging briefcases in a park, which is exactly what we do. We need a tamper-proof channel to get a unique individual secret key from the factory to a field device. But our device was made in the factory, so we put the key in the device on the assembly line and then ship the device. That way, the way I achieve that in my project is again using SaltStack during final assembly test. We run the tests, we assign an identity to the device, provide it with a security certificate, and then put it in the box. So we have a trustworthy, secure communications with remote devices, which allows us to send digitally signed software updates that the device will trust because they're signed with a certificate that it has carried around inside itself since it left the factory. So we have a secure way to get updates out to devices. The next thing we want to do is keep track of which versions each device has and which are available. Well, it turns out we get that for free from our container system. Docker containers have one or more tags which are intended for version identification. The tag you might be familiar with is the one called latest, which is the default tag that's used if you don't supply one when you ask for an image. Well, we can define a tag for staging and a tag for demo and a tag for debug and one for each developer and whatever else we need. And then permanent tags for each numbered version that we've shipped in the past. So now we know what version every device has running on it, and we have a way to request a particular version from the repository. So we are this close to continuous delivery right now. The last thing we need is to control which devices get which versions. Well, our orchestration system is also a configuration management system. And that has a pair of key value stores, one maintained on the server and one on the devices. So we can use the configuration management tools just as we would for data center systems to nominate what software we want on each device. And then the deployment tools give us continuous delivery from code through to devices. So we made it. We're deployed, but we're still not out of the woods. I'm working on some devices right now which are literally going to be set in concrete and expect to keep working for a decade. When they break down, you will need a jackhammer and some earmuffs to fix them. So let's think about flash memory. Each sector can only sustain about 100,000 write cycles before it becomes an X sector. So you don't want to be indiscriminately writing to your disk. So some of the things you should think about are turning off file system access timestamps, not writing log files to flash memory. Linux systems have had an ability to boot to RAM disk for a long time, which is often used on RAID systems. You can turn it on your embedded systems, which means if the part of the disk goes bad, you've still got a way to boot up. But say your concrete encased device goes into a crash loop. Well, the way I deal with this is my systems send out a DHCP request at boot time. Now, typically there's no server responding to that, so they fall back to their configured IP. But if a server does respond, then they use the public key certificates that they have to verify that they trust that response. And if so, they drop into a mode where they run a login server, and you can log into them with a password that you supplied to it over a secure channel, and you then have the ability to repair or reinstall the system. So that's some of the things that a device can do to look after itself. What else do we have in our bag of tricks? Well, our orchestration system includes some beacon facilities that transmit basic performance data. So our management system can provide a report of devices that have gone silent. In the event where a device is still alive but has a component failure, we can be a little more helpful and have it call attention to itself. When every light bulb in a building is a self-aware computer, or every smoke alarm, or every lamppost in the street, a little bit of help working out which is the one that's broken is very handy. Now, in the case where devices aren't online all the time, how do we manage updates then? Well, Amazon's IoT does a good job of this, where it provides synchronization tools for offline devices, but we can do the same thing with an orchestration system. In SaltStack, there's a component called the reactor, which responds to defined conditions. So we can trigger actions to occur when a device connects, and in particular, we can do things like check for pending updates. So next I want to consider, what if there's a problem that we can't fix with software? Maybe the fire alarm got stuck on at 3 o'clock in the morning. You want to be able to shut down components that require physical repair rather than have them become a danger or just a nuisance. So if you can build the ability to switch off subcomponents into your systems, then I think you should do that. And finally, what if a device is out there and you're done with it? You no longer want to support it. There's a space probe orbiting Saturn right now that has about 20 kilos of plutonium on board as its power supply. It's running out of rocket fuel, which means it's going to lose control and someday smack into a moon. Now, since we think that there could be life on some of those moons of Saturn, it really wouldn't be neighbourly of us to give them all tentacle cancer. So in a few days, it'll use the last of its fuel to kamikaze dive into Saturn itself. Now, if you're building devices that could outlive your software support, I encourage you to think about that situation. The problems recently with factories and businesses still using abandoned Windows XP systems shows us that if you can't patch it, you should unplug it. One simple way to do this could be to stop updating the security certificates or put out revocations for them. Okay, so we're coming to the end. The last thing I want to talk about is the data being emitted from your things. I mentioned that the orchestration system I use sends a heartbeat up to the server. So that allows me to visualize the availability of systems. I talked about flatliners earlier. We can also collect longitudinal information on availability, and that could be of interest when we have service level agreements that we need to meet. I also configure my devices to transmit their CPU and memory usage stats every so often, 15 minutes, an hour, it doesn't have to be too quick, as part of that post-release testing regime. If you put out a release that has a memory leak or a CPU tailspin, then hopefully your longitudinal performance data will tell you about that before the devices become dead. Now right now I'm just dumping all this data into an Elasticsearch database and I eyeball it from time to time, but there's many other things you can do about that, and I've put some links to other presentations on that subject in these slides. That image there, by the way, is the control center for the Brazilian Football World Cup from last year. So once again, we have reality outdoing supervillains. Now, one of my clients puts mesh networks into aged care facilities. So you have maybe 50 or 100 sensors which talk to a local gateway that has a cellular uplink. So the logs from the whole caboodle funnel back to the cloud, and the device keeps the last hour or so in memory in case a technician needs to look at it. So that's the data from the system software. And we can use those same mechanisms for the application software, or we can do something bespoke. So the first option is to use the message bus that is maintained by the orchestration software. Now, for SaltStack, that's a message transport called 0MQ, which is quite fast, quite lightweight, can carry a fair bit of data. So I think that's usually a good idea. I've done it as a proof of concept. I haven't deployed a product using that yet. And one of the good things about using that is you've got command line tools on your device to inject messages. There's quite a comprehensive Python library to talk to the message systems. If you want to get more fancy, you can write modules to extend the orchestration system both on the client and the server to inject custom status messages and do useful things with them at the other end. My approach to instrumentation is basically to overshare. I think it's better to have logs and not need them than to need them and not have them. The project with the subterranean sensors is fairly low volume, so I send that data up the orchestration bus. And at the master system, there's a rule that pulls it out and forwards it into my Logstash cluster. There's another project that I'm working on that has significantly higher data volume, and for that I wanted a separate channel. So those field devices run an MQTT message broker, and the Cloud Hub connects to each broker at each site and receives the big fire hose of data back from the lot of them, and it feeds that river of data into our data lake. So, very briefly, I want to talk now about visualization. We've already looked at system performance data, so I won't say too much more about that. And certainly system administrators have known how to visualize their performance data for a long time. But what people measure less often is the bottom line. Would you know if whatever makes you money stopped working? Does anybody remember a telco called OneTel about 15 years ago? Their billing system was not very good about issuing bills. Oddly enough, they went bankrupt. How long would you stay in business with no income? But broken is not always as simple as on or off. So sometimes you know that normal is within a certain range, and if things are not normal, you probably want to know. And data analysis tools that can do that are big business. There's a ton of them to choose from, and the best way to pick one is probably to go out there to the exhibition and see who's got the best swag. If you're interested in rolling your own, have a look at a system called Node-RED, which is a data flow processing system targeted at IoT. I've done some presentations on it. There's a link there in the slide. The last two things to consider are the long-term trends in your KPIs. Are you gradually going bust? Are you gradually going boom? And finally, there could be parts in your devices which wear out. Now, your flash storage and your battery are the two that spring to mind. So you might want to consider tracking some metrics about their long-term performance. Batteries in particular are an area where there's lies, damned lies, and manufacturer specifications. So let's summarise what I've talked about. We've looked at the threat landscape. We've worked through the product lifecycle from development through to testing, deployment, management, and retirement. We've covered some things that you can do with the data that comes out the end. And if you want to hear more about that next point, come along to Yao Data conference here in Sydney in September, where myself and also some very smart people will talk about data. So thank you for your time today. I am very happy to take questions in the 10 minutes or so we have remaining, and I will be here all week if you want to have a longer chat. So thanks again, and over to you.